AI image generation just crossed into a more controllable phase. Fewer hallucinated samples, better use of compute, and cleaner composition of multiple learned concepts. That matters because the bottlenecks are shifting from can the model generate to can it stay on manifold, spend capacity where signal exists, and combine edits without collapsing identity. These papers all point to the same trend. Diffusion systems are getting smarter about where to pay attention and where to suppress noise. Keep watching, because the details here reveal what actually improves fidelity in practice. Let's explore the first paper, Score Control for Hallucination Reduction in Diffusion Models. Score Control for Hallucination Reduction in Diffusion Models from the University at Buffalo argues that hallucinations in diffusion generators arise when the learned score field is overly smooth, which leaks non-zero probability mass into off-manifold regions. The paper formalizes this with a lower bound on model density outside data support that depends on the score Lipschitz constant L and score magnitude bound S, then introduces variance-guided score modulation, or VSM, an architecture-agnostic training objective that penalizes small score Jacobians using the variance learning head from IDDPM. A time-dependent schedule amplifies this penalty near the final denoising steps, where hallucinations are most likely. On synthetic and real image benchmarks, including 1D and 2D Gaussian mixtures, hands, 1, 1K, MNIST, shapes, cards, chess images, and ImageNet, 1K, VSM consistently reduces hallucination rates while preserving or improving fidelity and diversity. On these synthetic mixtures, it lowers score RMSE and hallucination rate. On hands, 1K. It cuts hallucinations from 23.33% to 5.15% for DDPM and from 29.5% to 21.15% for text-conditioned LDM. On cards, it reduces hallucinations from 22.41% to 2.33%. The paper also introduces chess images with an extreme semantic space of about 1044 valid board states to enable rule-checkable hallucination analysis and show that VSM increases valid novel generations rather than merely memorizing training boards. Let's explore the second paper, Show the Signal, Hide the Noise Spectral Forcing for Pixel Space Diffusion. Show the Signal, Hide the Noise introduces spectral forcing, a parameter-free input adapter for pixel space rectified flow diffusion that applies a time-conditional 2D DCT low-pass mask before the patch embedder, expanding its cutoff toward the identity at the data endpoint. The paper's core claim is that pixel diffusion wastes capacity outside a frequency-time wedge where the denoiser is only learning deterministic baselines rather than modeling the data distribution. On ImageNet 256, using JIT 700M32 with 64 tokens, spectral forcing reduces FID from 24.19 to 20.68 and raises inception score from 83.28 to 93.96 inches, a 6-0 epoch apples-to-apples comparison, with gains that persist across checkpoints and reach 15.15 FID at 120 epochs, matching a previously published roughly 145 epoch reference sooner. The method is regime-dependent. It helps most when patch tokenization is coarse and high-frequency content is mostly noise, remains competitive at 256 tokens, and can hurt when high frequencies carry essential signal. The same on-change operator transfers to SenseNova U1, a unified text-to-image model from the NTU-linked authors, improving DPG Bench and Genevol, which suggests the spectral prior is useful beyond class-conditional generation. Let's explore the third paper, Training-Free Multi-Concept LoRa Composition with Prompt-Aware Weighting. This Kingston University London paper tackles a practical failure mode in stable diffusion LoRa personalization. When multiple concept-specific LoRa adapters are composed, naive weight or output averaging causes concept interference and identity loss. The authors propose two training-free decoding time methods, W-switch and W-composite, that assign each LoRa a prompt-aware importance weight from the target prompt's text encoder embeddings using either prompt ablation weighting or prompt trigger weighting. W-composite blends all LoRa noise predictions with fixed normalized weights, while W-switch allocates diffusion time steps proportionally and preserves the character LoRa during the final 5 denoising steps to protect facial detail. On the composed LoRa benchmark with stable diffusion V1 and 5 and the realistic vision V5, 1 checkpoint, W-switch achieves the strongest overall results, reaching 75.14 ICLIP, 50,74 IDNO, 53,6 IARC face, and 36.54 T-clip average scores, outperforming LoRa switch, LoRa composite, and CM LoRa. The paper also introduces a more faithful image-based evaluation protocol that uses SAM3 or fan cropping plus clip, Dynov2, and arc phase similarity against real reference images, avoiding the centroid bias of text-based or global embedding metrics. In a mini CPM V assessment, W-switch scores 8.641 average across element integration, spatial consistency, semantic accuracy, and aesthetic appeal, and a 1/6 participant user study preferred it in 47.32% of trials, with statistically significant gains over all baselines. That's a wrap on today's AI paper highlights. Thanks for watching.